Welcome back. In this video, we're going to be covering another problem called best time to buy and sell stock. So, let us get started. So, the problem statement is as follows. Say you have an array for which the ith element is the price of a given stock on day I. If you're only permitted to complete at most one transaction, so you can either buy one and sell one, or you could just not do any transaction. You're asked to design an algorithm to find the maximum profit, so it's an optimization problem, to find the maximum profit that you can make from these stock prices. So let's take a few examples just to understand what the problem is really asking. So let's say we have an input of 715364. That means that the stock on the first day was $7, second day $1, third day $5, and so on. Now, if that's the input, then our algorithm should return 5 because the maximum difference is if we buy stock on the second day and we sell the stock on the fifth day, when the price is at 6. So right here, so if we sell it here and we buy it here, then we make a profit of 5. Note, however, that it's not 7 minus 1, because if I buy here and I sell here, then I make a loss of 6. So it's not a profit. I've lost money because I bought with high money and I bought for low money, so that's a loss for me. So we want to maximize the amount of money that we can make, or let's take another example. For example, if the numbers are in descending order, like 7, 6, 4, 3, 1, then that means that you cannot make any money. If I buy it here, then if I sell it here, it's going to be a loss. If I sell it here, it's going to be a loss. Again, if I buy it on 6, then it's also going to be a loss regardless of where I sell it. So whenever I buy, whatever date I buy here, I'm always going to make a loss. So I might as well not do any transaction here. And so I should output 0, because in this case, no transaction is done. So the maximum profit that I can make from this array is basically 0. I cannot make any money. But we don't want any losses, right? So we just don't do any transactions and we don't lose any money. Note also that the question asks for only at most one transaction, so you cannot buy and sell several times. So now that we understand the problem, let's start thinking about the solution. So a recursive solution that might come to our mind is to define Ri as the maximum amount of money you can earn from day 1 to day I. So there are two cases here which might happen. The first case is we sell at day I. So we've already bought before and we sell at day I, or we don't sell at day I. So whatever we bought before, we leave it and we don't sell it. So let's consider both cases. If you sell at day I, then you can find the minimum values from day 1 to day I so that you can make a maximum profit. So Ri is equal to price I minus the minimum of the previous prices. Now what does that really mean? If I'm going to sell on day I, then I want to look, so I'm on day I here, right? I want to look at all the previous days, find the day with the least price, choose that day, so that my price, if I'm selling on day I, so price I minus that price on that day, let's say it's day J, then this price is maximized, right? Because I'm selling, I want to minimize the minus here, right? So that my profit is maximized. So let's say this at the price today is 10, then I want to find the minimum one here. Let's say the minimum one here is 1. Let's say I have 1, 2, and 5 here. Then I want to find the day for which the least amount of that with the minimum price in the previous days, so that I can sell it on that day and I make the most profit, 9. But if I sell it, for example, here, then I would only make 8. So that's why I choose the day with the minimum price, and I choose to sell at that date. So if I do sell at day I, then I make the profit Ri equal to price I, the price today, minus the price with the minimum the minimum price in the previous days that have passed. Now what about if I don't sell at day I? Then the maximum amount of money that I can make is basically Ri minus 1. So it's right here. So this is I minus 1. And so Ri minus 1 is the maximum amount of money you can earn from day 1 to day I minus 1. So recursively, we find that the maximum amount of money that I can make is just Ri minus 1. Now, so we combine both of these cases to say that Ri, the maximum amount of money that I can earn today, is the maximum between Ri minus 1, the maximum amount of money that I can make in the previous I minus 1 days, or price I minus price I minus 1 all the way to price 1, which comes from here, that if you're selling on day I. So that's our recurrence relation, and we of course have a base case of R1 equals 0. If I only have one, so if I only have one element, like 1 here, or 2, one element, then the maximum profit is I buy on that day and I sell it on the same day and I don't earn any money. So that's why R1, if I only have one element, then the base case is I don't earn any money. I can't make any money because there's only one day, right? Now let's look at the recursive solution code. I'm going to include IOStream and vector, and using namespace standard, I'll define the function R, which takes an argument of I and a vector of prices. So I check if I is equal to 0, return 0, right? That's our base case. And then I set up int max value equal to Ri minus 1. And then for int j equal 1 to I, set max value as the maximum of Ri minus 1p and pi minus 1 minus pj minus 1, which are basically the prices at pi and pj. And take care that it's minus 1 here because C++ starts counting from 0th index. So that's basically the same recurrence that we derived at the previous slide, but it's basically put in a programmatical way. So we're changing this into code. Finally, I return the maximum of all of these, of maximum value of Ri minus 1 and pi minus 1 minus pj minus 1 all the way down for j from 1 to I. And then I return the max value. So I'm testing it here. I'm testing it on a few inputs that we showed at the beginning, the 2 examples, and it gave me the correct answer. You can test it on your own, and the code works. Now the time complexity of this algorithm is actually O(n) squared solution, and surprisingly, it's the same as the naive solution. So that's not really the naive solution would be check all the possible pairs, right? So check, let's say I want to do 2 loops, and I check for all the possible combinations, right? It's a brute force solution. I check at I at like day 0 and day 1, and I say, okay, how much profit can I make here? 1. Then okay, 0 and 2. How much profit can I do if I buy on this day and sell on this day? And you try all the combinations, and that's going to end up being an O(n) squared solution. Now surprisingly, this recurrence is actually O(n) squared solution, so we haven't really done anything. So can dynamic programming take down the efficiency a bit? And let's see. So the solution by dynamic programming would be let R0 to n minus 1 be an empty array of size n, and R0 equals 0 again, that's our base case. Now we go for I equal 1 to n minus 1. Ri is equal to Ri minus 1, which is the first case. Then you go from R for j equals 0 to I. Ri is equal to maximum Ri, or Pi minus Pj. That's the same recurrence relationship we did before. And finally, we return Rn minus 1, the solution for our problem. But again, this solution is O of n squared. So even with dynamic programming, we cannot take down our solution from O(n) squared. So we need to start thinking about what we're doing wrong here. Consider this inner loop right here. What we're doing every time is we're going all the way back. So we're fixing I, right? I is fixed here. So I is fixed here. We're going back and we're finding the minimum value of Pj in the previous ones, from j equals 0 to j equal I. So let's draw drawings to see here. So let's say I'm on the ith element here, right? So that's the ith element. So every time I go back all the way to 0, so that's the 0th element right here. So every time I go all the way down, and I'm checking for the elements, and there are a lot of elements here, right? I'm checking for the element with the minimum price, and I choose it. So the question we ask ourselves is, why do we have to go all the way down? So when I switch to I plus 1, so when I'm considering to I plus 1 here, again, so I plus 1, I'm going to be going all the way back to 0 again. So the question we should ask ourselves is, why do we have to go down all the way constantly, go down repetitively? Why don't we just store the minimum value in another variable? So instead of going all the way back, we know the minimum value right away. And that should give us the best solution, as we're going to discuss it now. So first of all, we're going to show this is the O(n) squared solution. You can look at it if you want, but that's basically still the O(n) squared solution, exactly like the naive method. We have an int n here, we set up the base case, we set up the vector here, which will store our result. We do Ri equal Ri minus 1, and we go from the loop. It's exactly like the pseudocode that we just showed, and we return Rn minus 1 here. And then finally, we try it on the same inputs, and it works very nicely. It gives us the correct answer. So we just discussed an optimization, a way that we can improve this solution from an O(n) squared solution and maybe take it down. So let's have a look at the optimized dynamic programming solution, right? So first of all, we let R0 to n minus 1 be an empty array of size n, and we set the base case as R0 equals 0. But this time, we're going to introduce a variable called minimum value, and we set it to the price at the first one, right? At the first day. And then we go for I equal 1 to n minus 1. First of all, we update the value of minimum value. So the minimum value is the minimum value of the current minimum value or the current PI, right? So if we draw it again, we would have something like, okay, we have an I here, right? And let's say in the previous ones, the minimum value was at day j. So that's day j here, and that's the minimum value, right? So at the start of at I check the minimum value is the minimum of the minimum value, which is this value right here at j, price j. So this is price j, and the price at I, and I update its value. Next, I set Ri is equal to the maximum between Ri minus 1. So the maximum price is either at the previous I minus 1 elements, or it's actually Pi, the price at I, minus the minimum value, whatever it is, whether it's this minimum value or it's actually I. So Pi is equal to Ri is the maximum of both of these values. Finally, once I'm done with that loop, I simply return Rn minus 1, And after this optimization, after we've noticed this optimization, the solution is actually an ON solution. There's only one loop happening here, and so the solution is O of n. And all the operations here are O of 1, so the whole thing is an O of n solution. So we've looked at the recursive, so let's recap really quickly. We've looked at the recursive solution, which was ON squared solution. We tried changing it into a dynamic programming solution, and it was an ON squared solution. The naive way was actually ON squared solution, and it looked like ON squared was the best we can do, but suddenly we noticed this observation about the minimum value, about the second loop that we were doing, and we said, hold on a second, why do we have to go all the way back to 0 to check for the minimum value? We can just keep updating the minimum value as we go. And that's what this observation was what took our solution from an ON squared solution to an ON solution, which is here the optimal way you can solve this problem. So, as a challenge or as a homework, try and change this pseudocode into a C++ code and post it in the question and answer section, and I'll try to look at your code. Hopefully it should be very straightforward from this pseudocode to translate it into a C++ code using a vector. You just write a function with a vector and a loop. Hopefully it should be okay to do the solution. Post it in the Q&A section. I'll have a look at it, and if there's anything, I'll let you know. And yeah, I hope you enjoyed the video, and I'll see you in the next video.